So now that we've seen examples of what valid arguments look like and kind of how to identify them using an Euler diagram, I want to look at some examples of arguments that are invalid, so you can see what that scenario is going to look like. And the thing you have to remember is that for an argument to be valid, it has to always be valid. We have to have no choice but to put, we've seen all the arguments so far have ended with our putting a final dot on the diagram somewhere. We have to be forced to put that final dot in a place that supports the argument's conclusion. If there's any possible way I can put that dot somewhere that does not support the conclusion, then the conclusion isn't always true and the argument is invalid. All right, so let's look at this situation here. All right, all people over 15 can drive. Susan, a specific person, is under 15, therefore she can't drive. All right, so let's say I've got two classes of people here, right? I've got people who are over 15, and I've got people who can drive. And everybody in the over 15 group belongs to the can drive group. So I'm going to do a circle here for people over 15, and I'm going to do another circle here for people who can drive. All right, now where am I going to put Susan? Well, I know she's under 15, which means I cannot put her in the over 15 circle. So just kind of cross that out. That area in there is off limits. I got to put her somewhere else. All right, well, I have two options here, right? I could put her here, or I could put her here. Well, which one do I pick? You have to pick the one that's worse in terms of, is the conclusion true or not, right? So it's possible for Susan to be here. It's possible that she is within the can drive circle. And if she is, then this is false. So that does not always, under all circumstances, have to be the conclusion. Doesn't have to be true. Therefore, this is an invalid argument. Again, kind of thinking back to what we talked about in some previous lectures, this scenario right here, that is our counterexample, right? The existence of that one possible situation where the conclusion is false is enough to make the entire argument invalid. All right, now before we move on, I want to parse this out a little more here and see if we can take this and turn it into a logical form. All right, so let's see. I'm going to rewrite this and think of this as for all people X. Well, let's stick with X. For all people X, if X is over 15, then X can drive. So you can kind of start to see the P and the Q now, right? Person is over 15 is P of X. The person can drive is Q of X. All right, so Susan is a specific person, right? So I'm going to let S represent Susan, and P of S is false. Right? P of S is not true because she is under 15. Therefore, what is our conclusion? Our conclusion is, therefore, Susan can't drive. That's not Q of X. All right, so hopefully you see what's going on here, right? We started off with P implies Q, not P of S, therefore not Q of, that should be an S right there, not an X. Right, so this is an example of the inverse, right, of the original universal conditional statement, and that's where the name of this comes from, right? This is called an inverse error. All right, so we've got another one here for us to look at. We're talking about functions this time, right? It's a little more mathematical. And my statement says all polynomials are continuous. Now, I've been assuming that everyone in the class here has finished a calculus class, so you know what continuity is, you know what differentiability is, those basic first semester calculus ideas. But I want to emphasize to you that it doesn't matter if you know them or not, right? Even if you don't know what it means for a function to be continuous, we can still evaluate the validity of this argument purely based on the techniques we've been talking about in the last series of lectures. All right, so I'm gonna draw my circles here, right? I have two categories of functions. I have polynomial functions and continuous functions. And I know that all polynomial functions fall into the continuous function group. All right, so this is what my diagram looks like. Right now, I know that f of x is continuous. All right, so I'm gonna just call this f. Right, I have a specific function here, f of x, so that's going to be a dot in my diagram. Where do I put it? Right, well, I know it has to go within the outer circle, right, within the continuous circle, which means, again, just like we saw on the previous slide, I have two options. I could put it here, in which case it is a polynomial, or I could put it here, in which case it isn't. And again, if I can come up with one possibility, one example where this is not true, then the whole thing is invalid. So because it's possible that my function is here, inside the continuous circle, but outside the polynomial circle, I'm going to have to conclude that this is also an invalid argument. Okay, so again, hopefully you're kind of seeing what's going on here, right? Notice I've got continuous here, and then I assume something about continuity, and I've got polynomials here, and that was up here in the premise. So again, if I want to kind of rewrite this, right, thinking of this in a logical form, right, I could say if f is a function. Now, we want to make this look like a universal conditional statement, right? So say for all functions, if the function is a polynomial, that's going to be p, then the function is continuous. So if I let the function is a polynomial, that'll be p. The function is continuous, that will be q. What I have here is for all functions, p of x implies q of x. Then what did I do? Q of x, or remember a function is continuous, that's q. Q of x, then p of x, and this has kind of that same form, if you will, of the converse of a universal conditional statement. So what we've seen here, again, kind of mirroring what we saw on the last slide, this is an example of what's called a converse error. Okay, so this ends our discussion of logic, kind of logic for its own sake, right? Logic as an independent subject. Going forward into the next chapter, we're going to switch gears a little bit. We're going to start talking about number theory, right? Another subject that comes under the discrete math banner. And we're going to really, we're going to talk, number theory is important in its own right, especially if you're going into computer science. It's an important part of cryptography. But from the perspective of a discrete math class, it's also a really great vehicle to illustrate basic concepts around writing mathematical proofs, right? So we're going to approach it from both of those directions throughout the next chapter.